potential evapotranspiration, which is the draw of water from the surface, and it's largely a function of temperature. Not entirely, but largely a function of temperature. Also, wind, relative humidity, solar radiation all play in this drawing of water. Remember, 80% of our precip is lost through this process. This is the current situation. Lots of blue on this map with a little bit of yellow. So we have potential evapotranspiration values, in the neighborhood of sort of 800 to 1,000 on the valley floor here. These two maps are projections of the future using two different climate change scenarios and two different global circulation models. The one on the left here is the so-called best case low greenhouse gas environment, which would see an increase in PE to over 1,000 here in the lower part of the valley. And on this side, this is the sort of business as usual scenario, but really not that much different. Again, 100 to 200 millimeters of potential evapotranspiration. So either way, we know it's going to go up. Just for comparison for you, the American Southwest, Phoenix, the valleys of Southern California, the desert country, it would be having potential evapotranspiration rates around 1,500, 1,600 millimeters currently today. So it takes us really closer to true desert conditions. We won't really have to stretch the facts so much in the future. We really will be a desert. And they can really call places the Sonoran this and the Sonoran that, and we'll be much more like the Sonoran. I don't know what it'll be like in the Sonoran desert at that time, but it'll probably be something even further out there. So very high potential evapotranspiration rates, even if we have slightly more precip. And you remember those trends seem to indicate that in a highly energized future climate, we might have slightly higher precip, but we're going to have much higher evapotranspiration rates, meaning that our moisture deficits will be higher at all elevations, particularly higher elevations. And, it still kind of gives me chills when I look at these pictures of that Okanagan mountain fire burning. But that was exactly the situation in 2003, where we had low precip, high temperatures, potential evapotranspiration values up there over 1,000 millimeters that year. And it's even at high elevation, even above that red line where the annual moisture deficit doesn't exist, still dries out, and we get burn baby burn at high elevation. Added to that, of course, is the issue with the insect damage, the pine beetle leaving potentially materials that are ready to burn as well. So this is really kind of the transformation of our forests, and we'll see it through insect and fire. That's how that transformation takes place. So that's the link to forest fires and potential evapotranspiration. I think we will have to be more vigilant than ever about our forest fire management regimes. Flooding, landslides, and debris torrents. I just want to make this point that these are events that are triggered more by extreme conditions, extreme events, than they are about long-term seasonal changes. And I think Bob will talk fairly extensively about extreme events, whereas I've been speaking to you pretty much about long-term trends and seasonal trends. That climate change may be expressed by change in both the occurrence and the intensity of extreme events, and we are susceptible here. We live in a mountainous environment. Remember earlier I talked about alluvial fans. This is the Golden Mile here, and these green areas are alluvial fans that emanate from these, the three sisters, Testalinden and Hester and Tinhorn Creek. Testalinden went out a couple of years ago, largely as a result of a blocked outage in an upland reservoir. But Tinhorn Creek flushed out not that long ago, before the vineyard was established on that fan. But there was a debris torrent that came down Tinhorn Creek 35 years ago, that if it had happened today and it was entirely a natural event, would have created substantial damage to the vineyards and infrastructure on the Tinhorn Fan there. Slight aside here, the viticulturalists love the fan. I guess because I work for Agriculture Canada, I got to keep bringing this agriculture stuff in. And I'm also a soil scientist. So the fans, they love fans, and they love to work on fans for two reasons. One is that the material is coarse textured, so they get good drainage, and they can manage irrigation water and soil water levels effectively. But the fan shape is slightly convex, slightly elevated above the valley floor, so it sheds cold air. And it alleviates any issues they get with, shoulder season frosts. So the fans, although an active land farm, are really one of the land forms of choice for the viticulturalists. And then on this side here, this is a map I just got from the Ministry of Environment. It's part of their terrestrial mapping series. This would be Karameas right here. This is the Similkameen River and the Ashinola River coming in here. And just wanted to show you all of these areas that are marked in purple striping are slopes that are considered to be subject to landslide and erosion. So these are very steep slopes in that part of the country, and with some sort of extreme event, in some sort of heavy precipitation event, these slopes are quite susceptible to move. So there's lots of those, and then in the blue on the valley floor, this marks the extent of the active floodplain of the Similkameen River, and these are areas that could potentially be flooded if we were to get some kind of peak flows occurring. So geomorphically, a dynamic landscape in the Similkameen Valley, and lots of things to consider there in terms of interaction between climate and materials. Just a couple of things on projected change in precip and snowfall. Basically, as I say, looking ahead to the end of the 21st century, this dark line here projects kind of the middle estimate, 8% increase in precipitation. But on this one here, this line projects the proportion of that upland precip that will fall as rain rather than snow. So about 25% change in the way that we'll get more rain and less snow up there. This will cause a change in the hydrograph. In other words, the flow regime of these tributary streams that are coming out of the upland. We have here in the dark line, the sort of baseline, and this is conceptual. I think it's modeling from Chapranye Creek in Peachland. But basically what we're going to see, the current situation, we have a peak flow that occurs sometime in May and drops off rapidly, so that by August, many of these tributary streams have very low flow, and on some years no flow. What we'll see in the future with this change in the snow to water is that rather than storing water as snow and then having it all come blasting out of here during the melt season, we'll have a hydrograph that looks more like this, with a lower peak flow, a more extended peak flow, but a much earlier peak flow in late March or early April. And so that creates a challenge for the water purveyors in the sense that storage will then become more critical. Less will be stored up high. It will come down earlier in the year. More of that will have to be held, because the time when people want to use water, of course, is out here when the flows are very, very low. So this is the impact of this change in precipitation regime. So back to this figure again. It's the same one I showed earlier. The dotted red line is the one standard deviation below the long-term mean inflow, and could be one way of defining drought. And believe it or not, defining drought is, in this environment, it's not always that easy. My colleague Denise says, well, in agriculture, we have no drought. We never have a droughty year in agriculture in the Okanagan because we irrigate. Doesn't really matter what precipitation is. But I think in terms of the broader hydrologic cycle, and particularly if you're talking about forest management or sort of upland activities, then drought really is those years where we get these very high P minus PE values, and that translates into lower inflow into the lake. So looking at this, if you take the 3-year Dust Bowl period out of the equation, we definitely see more of these low inflow years in the last 50 years than we did in the previous 50 years. Yet it's highly variable, and in fact, the last number of years, this only goes out to, I can't see that. Yeah, we've had some high inflow years since 2006, but this is one way to define drought. Somewhere in the neighborhood of 500 million cubic meters, plus or minus quite a bit. In 2003, the inflow was only 123 million cubic meters, so well below the average. And as I pointed out, the severest drought was between 1929 and 31, and at that time, the inflow in 1929 was only 80 million cubic meters. We could see that again in the future. And as I say, the modeling based on projected climate shows this narrowing of supply and demand and the increased frequency of drought years. This is, again, the other side of it, the demand for water, irrigation. Now there's just a cloud of points there from many, many different models run with different scenarios at different time frames. But again, it's the trend line here. And we do see increasing demand because of higher evapotranspiration rate from the irrigators. To some extent, we do expect that more increased use and developed technology in more efficient irrigation systems could largely offset this trend, and that's really the focus of much of the work that we do at the research station, is to try to develop irrigation systems that would flatten these lines right out. Even if it gets drier, we will be more efficient in the use of our irrigation systems. Again, in terms of the interaction, we don't see the same number of cold events that we used to see. Our winter cold events, much fewer than they used to be. This year here, this was the last time Okanagan Lake froze over completely. So it's been since 1949, 50, I think was the year. It was the last time. We've had a couple of cold winters where we've had minimum temperatures reach this minus 30, but much less out here. And it was a result of the warming of extreme minimum temperatures that has allowed the current wine industry to establish here in the valley. We could not have grown the vinifera varieties that we grow today even 30 years ago. Not because it wasn't warm enough in the summer, but because we had these low temperature episodes in the winter. And we don't see those as much. That's allowed that crop to establish. And by vinifera, this is the Cabernet Sauvignon. Prior to that, we were growing hybrid varieties that were much more cold tolerant. And lastly, so warmer winters, good thing in some ways, but I will tell you that our entomologists are really scrambling to deal with this spotted-winged Drosophila, which is an insect that has come up from the south. We've never seen it here before. Extremely damaging to tree fruits, and no real known strategies for control at this point, other than kind of going back to the bad old days of heavy use of various insecticides. So, there's the good and there's the bad side of it. This is a real challenge. Is this change in our insect population as things warm in the winter? It's these winters that make the difference. Okay, so there we go. The Okanagan similkameen, characterized by complex hydrologic supply and demand. This historic supply and demand equilibrium is currently under stress from many sources, both natural and societal. In the 21st century, we'll be forced to make significant concessions. I think we'll no longer be able to have it all. We won't be able to supply the fish with the water that they need, the golf courses with the water that they need, the sprawling subdivisions with the water that they need, and the irrigators. we will probably be forced to make some tough decisions. And on the positive side, it will require the human capacity for ingenuity, creativity, and adaptation, all of which we will need, but I'm sure that we have here in our community.